notes on key features of graphs. So we're going to be looking at end behavior. To save us a little time and everybody individually putting this in to fill in this table, I've gone ahead and done that in Desmos. So here in Desmos, I've put the function in a table for I have x and then the f of x. And these are the values it comes out as. So I'm going to go ahead and fill those in on this table in the notes, and y'all can copy that down as well. Okay, so this, the negative 10,000 is oops, I guess I should get my pen before I start trying to write. There we go. Okay, so it's 0.6666. So 4 sixes after the decimal. Okay, at negative 1,000, it's 0.666. At negative 100, it's 0.66. And at negative 10, it's just 0.6. Okay, so before I fill in the rest of the table, I'm just going to look at those values. I'm going to answer this first question, which says, what is happening to the values of f of x? So that's what we just filled in, as the values of x get very small. So as x gets very small, so I would say here, it's getting smaller and smaller and smaller, right? More and more negative. Do you agree? Okay, so as x gets very small means as we go to the left. So this means the left side of the function. Okay, so as x gets really small, what's happening to these values? So starting at 0.6, what's happening as I go more and more to the left? There, it is increasing in very, very, very little by little toward what number though? Is it if what's happening? How is the number changing? It just keeps adding another 6 in the next place value, right? So is that ever going to get to 1? No. So it's approaching 0.6 repeating, right? What is 0.6 repeating? What, like as a fraction? So that's 2/3. So would you agree that this is approaching 2/3? Okay, so we're going to say that it approaches 2/3. Okay, so now let's do the right side to answer this question. As the values of x get very big, so that means as we're moving to the right, so the right side of your graph. Okay, so those numbers were 0.73, and I mean it's 0.733. It's the 3 is repeating, but then it's 0.673. And then 0.6673, and then 0.6667. Okay, so what's happening here is that 7 and then the 3 repeating keeps getting pushed further and further back, right? Another 6 is coming in front of the 7. Y'all see that? Okay, so this is also going to eventually be approaching 0.6 repeating, isn't it? So it's also approaching 2/3. But y'all said on this side, the numbers were getting a little bit bigger. Over here, they're getting a little bit smaller, right? To go toward that. So it's also approaching 2/3, but it's coming down to 2/3. The left side was going up to 2/3. Okay, so to help you get a visual, we can sketch that. Bless you. Okay, so let's say 2/3 is here. Okay, so the left side of my graph is approaching 2/3 from underneath. It's coming up to 2/3 like this. The right side of my graph is approaching 2/3. It's coming down to 2/3. So it's approaching from over here like this. So what is happening at 2/3? What is that? Yeah, it's an asymptote. Okay, So the ends of my graph for this example happen to be approaching an asymptote at 2/3. Okay, so it's not always going to approach a number like this, approach a specific number. Sometimes the numbers will just be going up forever or down forever, like to positive or negative infinity, right? Okay, what we're looking for is, it's just called the end behavior. What are the ends of the graph doing? The left and right hand ends. What are they going toward? What are they approaching? What is the y value approaching? Okay, so here it says the end behavior and I'm going to mark out this word polynomial because yes, this is true for polynomials, but it's true for others as well. They don't have to be polynomial. That example we just did was what type of function? It's transformed from the reciprocal, so it's a rational function. Yeah. Okay, so it's not just polynomial functions. So end behavior of a function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. Okay, so as it approaches negative infinity, that's the left side of the graph. Okay, so as x goes to negative infinity, that means it's the left side, right? That's over here. X is negative infinity on this side. Okay, and as x approaches positive infinity, that means the right side. Because x is going to positive infinity over here. Y'all agree? Okay, so in layman's terms, what this is saying is when we're asked to find the end behavior, you're asking yourself, what's happening to y, or f of x? F of x is the same thing as y, right? Y'all agree? Okay, so what's happening to f of x or y as x approaches positive or negative infinity? So as it goes the left and right. Okay, so that's what end behavior is asking. That's the question we're answering. Now there is specific or special notation, the way that that's going to be written, that you need to be able to read and interpret, and you need to be able to write. Okay, so it's not going to be like up here where it says as x gets very small, f of x approaches 2/3. We're not going to write it out in words like that. Okay, so we're going to use this graph here as an example. We're going to do the notation. Okay, so I'm going to put as x approaches negative infinity. So that's written like this. As x, and then we use this arrow symbol for approaches, negative infinity. So as x approaches negative infinity, and what that actually translates to, what that means when you're looking at your graph, that means the left side. Okay, so as x approaches negative infinity, f of x approaches, we use that same arrow symbol, okay, and then we say what is x approaching. Okay, so as this graph goes, as we go to the left on this graph, what's happening to the y values? Are they going up or down or to a specific number? Down to negative infinity, right? So we would put negative infinity. Okay, so what that interprets to me is the y's are going down, so the graph is falling. So the left side is falling. That's the end behavior on the left end. Does that make sense? Okay, and in green here is the notation that you need to be able to read and write. Now on the right side, I would say as x approaches positive infinity, okay, so as we're going to the right, f of x approaches, so that's y. What is y going toward on this side? Infinity. It's going up forever, so positive infinity. Okay, and again, I would interpret that the right side. Whoa, I don't know what just happened there. Try that again. Go. Okay, the right side is rising. So I interpret as x approaches infinity, that means the right. F of x approaches infinity, that means rise or going up. So the right side is rising, the left side is falling, but what's written in the orange and green is the actual notation. You need to be able to write that in. Y'all feel okay about that? Okay. I was not thinking clearly when I put this together because I used almost the exact same shape. It falls on the left and rises on the right. So not the best second example. We are going to go ahead and mark through the table because these numbers get so small and so large here that I would have to use scientific notation to fill it in. And so we're just going to skip the table for now. We have the graph anyway. Okay, so we can just visually see what's happening on the left and right hand side. Okay, so this one would be, did I use green for left? I want to make sure, yeah. Okay, so if I were to give the end behavior here, I would say as x approaches negative infinity, f of x approaches negative infinity. That means the left side is falling. Okay, the right side is rising, so I would say as x approaches positive infinity, f of x approaches positive infinity. And like I said, I should have put a different example here since I already did one that had that end behavior. It will not always be the same. These are not always going to match. It's not like if this is negative, this is negative, and if this is positive, that's not the case. That just happens to be the examples we did. Okay, it's not always going to be an infinity. If there's an asymptote, like here, your answer, it would say it's approaching 2/3. Does that make sense? Okay, so we're going to go back in a minute and we're going to fill in our end behavior for all those parent functions we talked about last week. Okay, but first let's go ahead and knock out the last page about symmetry, and we'll do the symmetry and the end behavior on the parent functions once we finish. All right, so symmetry of graphs. Okay, there are two types of symmetry that you're going to see on our graphs. The one that probably you immediately think of or stands out is line symmetry. Okay, line symmetry means there's a line on your graph that you could fold it along, and every point on the left and right or the top and bottom of that line would all match up. Okay, it's like a mirror image on both sides of the line. Does that make sense? Okay, the two most common types of line symmetry, or the two that we're going to focus on, I should say, are these two in this key concept model here. So what line for this first image, this first model, what line could I fold this over for all those points to match up? Yeah, the x-axis. So the x-axis is a line. So if I can fold it over the x-axis and everything matches up, okay, I would say that this is symmetric with respect to the x-axis. Or you may hear it as symmetric about the x-axis. Okay, and again, that's a type of line symmetry. I'm just going to put that in the margin there. Okay, you don't always have to write out symmetric about the x-axis, symmetric with respect to the x-axis. I'll just accept x-axis symmetry. Does that make sense? There are algebraic tests, like if you had the equation instead of the graph, but we don't need to worry about that right now. We're going to have graphs. We just need to visually be able to tell if it has x-axis symmetry. Okay, or this one, what is the line for this second model that you could fold this along and everything would match up? The y-axis. Okay, that is also line symmetry, and it could be referred to as symmetric with respect to the y-axis, or symmetric about the y-axis, or you could just say y-axis symmetry. So far, so good? Okay, so those are two common types of line symmetry that we're going to be on the lookout for. Okay, the other type of symmetry other than line symmetry is called point symmetry. Point symmetry is when your graph can be rotated around a given point and appear unchanged. Okay, so you rotate it instead of fold it. So it's not reflectional symmetry, it's rotational symmetry. Does that make sense? Okay, so the type of point symmetry that we're going to focus on is using the point of the origin as the point that we rotate about. So if I were to put my pencil right here on the origin or my finger and rotate this paper 180 degrees, okay, so that would be turning it upside down, right? 180 degrees, okay? It would appear unchanged. It would look exactly the same, wouldn't it? Can everybody visualize that rotation? Okay, so that is a type of rotational symmetry. If I can rotate it about the origin, it has origin symmetry. Okay, and I'll highlight here, you may see it referred to the wording symmetric with respect to the origin or symmetric about the origin. Those all mean the same thing. Okay, so if I rotate it, point symmetry, using the origin as the point of rotation. Okay, what type of function is this? That's the cubic. So the cubic function, if it hasn't been shifted, that has origin symmetry. What function was this one here? Yeah, that's a quadratic. It's not the parent. This one's been reflected and shifted up, right? Okay, and it could maybe stretched, we can't tell. Okay, but it's still got y-axis symmetry. Once I shift this to the left or the right, though, it's no longer symmetric about the y-axis, right? It would still have line symmetry, but it's not the y-axis anymore once it shifts left or right. But shifting it up or down and reflecting and stretching it, it still had y-axis symmetry. All right, so let's look at these two examples here. We're not going to worry about the algebraic test or anything, just visually looking at these, tell me what type of symmetry do you see? Do you see one of those three that we just went over, X, Y, or origin symmetry? So for graph A here, what do you see? X-axis symmetry, good. Okay, so the line of symmetry is the x-axis. Okay, that is a form of line symmetry. Oh, I don't think I put in the margin. Oh, I did. I put that one was point. Good. Okay, what about graph B? Do you see any type of symmetry talked about? Origin symmetry, good. Symmetric about the origin or symmetric with respect to the origin. Okay, that is a type of point symmetry. Okay, if I put my pencil here and held it down at the origin and rotated 180 degrees, that would look exactly the same as it does now. Everybody good with symmetry? Okay. Now, odd and even functions, last thing we're going to talk about, okay, goes hand in hand with symmetry because functions that are symmetric about the y-axis, the right color here, I was using blue. Okay, if it is symmetric about the y-axis, okay, that is an even function. Okay, if it is symmetric about, I don't know what color I used for this. What did I use up there? Oh, blue. Oh, I thought I used blue. I used green. Oops. I'm just going to fix my color coding real quick here because these are the notes I'm going to post online. So green was Y. All right. So symmetric about the y-axis, it's an even function. If it's symmetric about the origin, we say that that is an odd function. Okay. Now, what about this one that we just did? Was this symmetric about the y or the origin? Okay. So if a function does not have the symmetry about the origin or the y-axis, you simply say that it is neither odd nor even. It does not have to be odd or even. It can be neither. Okay. Algebraically, there is a test if you have the equation instead of the graph. So you can't visually see if it's symmetric about the y-axis or symmetric about the origin. You could use this algebraic test, plugging in a negative x into the function. And you can see here in this little graphic, if you input a negative x and it comes out equal to the original function, so exactly the same, that is an even function. So if it comes out exactly the same, it's an even function. After you simplify, it comes back to the original. Okay, but if it comes out the opposite, meaning what was positive is now negative and what was negative is now positive, like all the signs just change, that's an odd function. Okay, we're not going to have to worry about that algebraic test for a while, but I wanted to go ahead and throw it in here while we talked about odd and even. Okay, feel okay about that? Symmetric about the y, even. Symmetric about the origin, odd. If it's not one of those, it's neither. Does that make sense? Okay, good. All right, now I want you to pull out the parent function notes from last week, that graphic organizer, this one right here. We went through all the parent functions and we left symmetry and end behavior blank. We said we would come back to those once we had taken those notes. So now's the time. Okay, so looking at our linear function, do you see any symmetry? X-axis, y-axis, or origin are the three we're looking for. Origin, if I rotated that 180 degrees about the origin, it would look unchanged. I don't know what's happening here. Why? Oh, here we go. Okay. So this one has, uh-oh, Word is not responding. Cool. Let's see. Now? No. I'm gonna see if I can close this and reopen it. Let me find the fifth period. There we go. This isn't what is happening. Keep slipping back to the other notes. Here we go. There we go. All right, what about end behavior here for the linear function? Okay, as x approaches negative infinity, so the left side of the graph, what's happening to f of x? What's it approaching? Also negative infinity, good. Okay, what about the right side of the graph? As x approaches infinity, what's f of x approaching? Positive infinity. I don't know what's happening with Word. Okay, there we go, good. All right, so everything should now be filled in about the linear parent function. Okay, absolute value. Do you see any symmetry here? Okay, y-axis symmetry, good. Now, that's for the parent function. If this is shifted left or right, it's no longer has the vertex on the y-axis. It loses that y-axis symmetry, right? Okay, but the parent function is symmetric about the y-axis. All right, end behavior. As x approaches negative infinity, so as the graph goes to the left, what's f of x going toward? Positive infinity, good. So here's one where those don't match. That one was negative, this one's positive. So the left side is rising. Okay, as x approaches infinity, what's f of x approaching? Also positive infinity. So both the left and the right are rising. Both ends are going up. All right, how about quadratic? Any symmetry? Good. Y-axis, same as absolute value. And the left and right hand ends are both rising, aren't they? So isn't it going to have the same end behavior as absolute value? Yeah, so again, the left side will be going up to infinity and the right side will be going up to infinity. Both the left and right are rising. All right, now square root, and I realized after this was all printed and we'd started, there's a typo here. This, as x approaches negative infinity, should not be there. X does not approach negative infinity in this graph. That is supposed to be a 0. Okay, so make sure you edit that. Okay, now, is there any type of symmetry? X-axis, y-axis, or origin? No. No. If I were to rotate this 180 degrees, that little curve would end up in quadrant 3, which right now there's nothing in quadrant 3, so that does not appear unchanged. It looks like it's flipped over. Okay, so this does not have any symmetry. Okay, but in behavior, as x approaches 0, so as we move to the left along this graph toward the 0, what is y approaching? Okay, I heard 0 and I heard negative infinity. Does the y value go past 0? No, remember the range here was 0 to infinity. So this is also 0. Okay, f of x is approaching 0 as x approaches 0. Okay, the right side, as x approaches infinity, what's f of x approaching? Infinity. It's going up as it goes to the right. All right, cube root, any symmetry? Symmetric about the origin. Okay, end behavior. This is the one, I think it got flipped with the square root one on your printed version. It's correct here on mine. It should be negative infinity. I believe on the printed one, it has the 0 there. So please fix that to be negative infinity. Okay, so as x approaches negative infinity, so the left end of the graph, what's f of x approaching? Negative infinity. So the left side is falling. The right side is what? Rising, so it should be approaching infinity. Still good on end behavior? All right, cube root, any symmetry? Good, origin symmetry again. Okay, as x approaches negative infinity, so the left end of this graph, what's f of x approaching? Negative infinity as well. Right side? Positive infinity, good. All right, exponential. Any symmetry? No, no symmetry here. Okay, end behavior. So as x goes toward negative infinity, so the left end of this graph, what is the f of x approaching? 0, good. It's approaching the asymptote. Kind of like that 2/3 asymptote in our notes. Okay, so this one is not infinity or negative infinity, it's a specific value. Okay, what about the right side? As x approaches infinity, what's f of x approaching? Infinity as well, it's going up. So the left side is approaching the asymptote at 0, the right side is going up, it's rising. All right, logarithmic, any symmetry? No. All right, the left side, as x approaches 0, because there's a vertical asymptote at 0, so x doesn't go past that. So as x approaches 0, what's f of x approaching? What's the y value doing? Going toward negative infinity. Good, it's falling. Okay, and on the right side, as x approaches infinity, what is f of x approaching? Very good. Y'all have got the hang of this. Last one. Any symmetry for the rational function. Origin symmetry again, that was in the notes. It was a rational function that they used in one of those examples. All right, what about end behavior? As our graph goes to the left, what's f of x approaching? Okay, yeah, it's 0. I heard negative infinity, but look at the graph closely. Here, the left end of the graph is going toward the asymptote at 0. Here in the middle, it's going toward negative infinity, but that's not end behavior. That's not the end of the graph. This is in the middle of the graph, isn't it? So left end, as x is approaching negative infinity, it's f of x is approaching 0. What about the right end? Also 0. Good. All right, so everything in that packet for parent functions should be filled in now. There on the back, there was printed a check for understanding. We are not going to worry about that. Some of those questions are much too complicated or difficult than you're going to be asked. So I'm not even going to ask you to do them for a check for understanding. So that doesn't make sense. You're not going to have some of the questions worded that way or have to do that. So that those 2 note packets are both complete now. If there is something missing, if you missed a day last week or yesterday, or you got up and went to the bathroom and missed an example, double check that anything missing gets filled in. The recording of the lessons are posted on It's Learning so that you can get anything you missed filled in. We're going to be doing some practice over this on our Delta Math this week. So make sure if you have not registered, created the Delta Math account, like we did that on day 1. So if you're new to the class or didn't do it for some reason, that needs to get done. And the instructions are on the home page of It's Learning. Okay, so make sure your Delta Math is good to go.